Okay, so let's move on to question number 15. So question number 15 is another application problem of the derivative. It tells us the following. A particle is moving along the x-axis with an acceleration given by a of t is equal to 6t plus 2, where t is measured in seconds and s, which is our position, is measured in meters. Now, if the initial position is given by s of 0 is equal to 3, and the initial velocity is given by v of 0 is equal to 4, and then the question is to find the position of the particle at t seconds. Okay, so this is a problem where we have to use the indefinite integral. How do we know this? Well, when we first began talking about derivatives, I told you that if you have a function, let's say s of t, this function is our position function. It tells us where the particle is, right? If we take the derivative, the first derivative, then that gave us the velocity of the particle. And if we took the second derivative, we took the derivative again, then that gave us the acceleration of the particle. In this problem, we are beginning with the acceleration. Somebody gave us the acceleration, meaning we are in this step. And we have to find the position, so we have to go up. Now, how did we go down? We went down by taking derivatives. Okay, we took derivatives here. To go back up, we have to take integrals. We have to integrate. We have to find the antiderivative. Okay, so first things first. Let's talk a little bit about our acceleration function. Our acceleration function is a of t is equal to 6t plus 2. To find out what, remember this is the second derivative, s prime of t. To find out what this is s double prime. So to find out what s prime of t is, we have to take the integral of this. When we take the integral of this, we're going to get s prime of t, which is going to be equal to really the velocity of t, which means that we have to take the antiderivative of 6t plus 2 dt. But remember, when we do this, we could do it by piece, or we could use the reverse power rule. If we do it by piece, this is going to be the integral of 6t dt plus the integral of 2 dt. And that was equal to, well, the integral of 6t dt, remember, when you have something like this, of x to the p dx, it's just going to be x to the p plus 1 divided by p plus 1. So here, if I take the 6 out, I just have the integral of t dt plus 2 dt. So what I have here is 6 times t squared divided by 2, because this is a power 1, plus 2 times t, because remember, when there's nothing here, this is like having t to the 0 power. So 0 plus 1 is 1. So we have 3t squared plus 2t plus c as our antiderivative. And I'm going to call this one C1. There's a reason I'm calling this C1, and you'll see it now. So the velocity of t, which we just found, is equal to 3t squared plus 2t plus c1. But I'm actually told what velocity at 0 is. The velocity at 0 is 4. So if I plug in 0 here for t, I get 3 times 0 squared plus 2 times 0 plus c1 should be equal to 4. But notice that 3 times 0 squared is 0, 2 times 0 is 0, so I get that c1 is equal to 4. So now I have that my velocity function is really 3t squared plus 2t plus 4. So that was my original velocity constant. And now I could take the integral of this to find the position. So I will take the integral of this, of 3t squared plus 2t plus 4 dt. The antiderivative of this is going to be equal to 3t cubed over 3 plus 2t squared over 2 plus 4t plus c. And this is equal to t cubed plus t squared plus 4t plus c, and I'll call this one c2. And that is equal to our position function s of t. But I'm also given information about the position. I'm told that at the initial position, s of 0 is 3. So I'll plug in 0 for t here, and that should give me 3. So I have 0 cubed plus 0 squared plus 4 times 0 plus c2 should be equal to 3. Well, that just means that c2 is equal to 3. So our position function s of t is actually equal to t cubed plus t squared plus 4t plus 3. And that will be the solution to our problem, because we have found a position function for t. Okay, so this is the solution. Again, what did we do? We took the antiderivative, then we solved for the c value at the points given. We were given some information to be able to actually figure out what those c's were, and then we integrated again to get the position. And then we again solve for that c. Okay, so this is a nice application problem that you could have on the final. Another way of getting this problem in the final will be to begin with the position and be asked to find the acceleration of a particle. So that's another way that you could see this problem. Okay, problem number 16, probably the problem that most people hate on the final. It's an optimization problem. We're told that a rectangular poster is to have an area of 100 square inches with a 1-inch margin on the right and left sides, and to each margin on the top and bottom. The question is to find the dimensions of the poster with the largest printed area. So find dimensions of poster with the largest printed area. Okay, so we know something about a poster. It's a rectangle. We know that the area of a rectangle is given by length times height, or x times y. And we know that this area is supposed to be 100. That's given. So it's supposed to have an area of 100 square inches. We know that we have 1-inch margin on the left and the right. So have 1-inch margin on the left and the right. Right? And we have a 2-inch margin on the top and bottom. Now, if the left and the right are given by our x and the top and bottom are given by our y, this is height, then what we really have here is that the dimension that we're looking for is going to be equal to x plus 2 times y plus 4, because 2 plus 2 is 4 and 1 plus 1 is 2. Because we're supposed to have these bigger margins here. Now, what happens here? Well, I have a function of 2 variables and I want to work with a function of 1 variable because it will make my life easier, and I have to optimize this. So what I will do is I will solve for one of the variables here. In my case, I'll solve for y, so I could just work with x's, and then I'll substitute back into this function down here. So I have 100 equals x times y. That means that 100 over x is equal to y. So this piece becomes x plus 2 times 100 over x plus 4. Now, if I wanted to, I could multiply through and simplify this a little bit, because eventually I'm going to have to take a derivative, so might as well multiply this now. So we got 100 plus 4x plus 200 over x plus 8 when you distribute all of this out. So you get. So that means that this is equal to 108 plus 4x plus 200 over x. And now we can take the derivative here. So if I take the derivative here, what do I get? If we take the derivative, we get, well, this 108 goes away. So we get 4 plus 200 times x to the negative 1. So that's going to be equal to negative 200 over times x to the 2. So let's change this. So it's going to be equal to negative 200 times x to the minus 2. And we have that is the derivative. So it's 4 minus 200 over x squared. Now, to find out what dimensions of the posters will have the largest printer area, we have to find the critical values of this. So to find the critical values, we do 4 minus 200 over x squared is equal to 0. We solve for when the derivative is equal to 0. So we're doing a prime equal to 0. So that means that we have negative 200 over x squared is equal to negative 4 by moving the 4 to the other side. We could cross multiply here, so we'll have negative 4x squared is equal to negative 200, which means that x squared is equal to 200. And then when you take the square root of that, you're going to have x is equal to plus or minus square root of 200. Now, because area is positive, we don't care about the negative answer. There's going to be radical 100 times radical 2, which is going to be 10 radical 2. So we have a value for x. The value for x that maximizes the area is 10 times radical 2. Now, what is the value for y? Well, I could plug in here into this for x and get a value for y. In fact, I could plug it right here because I already have it simplified. So I have 100 over what x is equal to, which is 10 radical 2, is equal to y. Notice that this is going to be equal to 10 over radical 2 here, because the 10s cancel out here. You just get a 10 up here. And now I have a value for y. And you could check that your solution works by plugging in here into 100x times y. So let's just check that our solution so far is working. We know that the area is supposed to be 100. We have a value for x, which we said was 10 radical 2. And we have a value for y, which we said was 10 over radical 2. When we multiply this out, the radical 2's are going to cancel, and 10 times 10 is 100. So far, so good. So far, the work that we have done is correct. Now, to actually find the dimensions, all you have to do is substitute up here. because remember, um, the the length is given by x plus 2, and the height is given by y plus 4. So you just have to substitute in. So x again was 10 radical 2, so we have 10 radical 2 plus 2 is going to be the bottom dimension, and the top dimension is going to be 10 over radical 2 plus 4. And that's what's going to maximize this this printed poster. And it will also give us the area that we wanted to, which was 100. Okay, so that is the solution for this problem. The most difficult part of the problem, to be honest with you, is just figuring out this relationship of x plus 2 and y plus 4. That is not easy to do, and it's not you have to get a lot of practice with these word problems to actually figure it out. So I do suggest going back on the homework of optimization and practicing that to be able to do this problem, because it's just practice. The more practice you do, the more you recognize how these problems are done and how each function is related to the problem for you to optimize it. But once you get the relationship, it's just a matter of doing substitutions and taking the derivative. So it doesn't become too bad once you actually have the relationship built. All right, so problem number 17. For problem number 17, we are asked to write but do not evaluate a 3-term Riemann sum for the integral from 0 to 1 of 1 plus x squared dx. Now, keep in mind what we define the integral as a limiting process of a Riemann sum. So we said that the integral from a to b of x dx is equal to the limit as the delta x's go to 0 of the sum of f of xi times delta xi as n goes from a to b. Now, what do we have here? We have a 3-term Riemann sum. So to write a Riemann sum, remember that we have to write it in this form. So, and it's a 3-term. We don't have to evaluate it, but we definitely have to write it. So first of all, a Riemann sum with 3 partitions, because 3 terms means 3 partitions, means that we're going from 0 to 1, and we are making 3 partitions. So remember, we have to make rectangles. So let's say we have a rectangle here, and they don't have to have the same height. Let's say something like this. It's not like this because this is what the function we're working with. Just for the sake of argument, this is what we're going to be dealing with. Each of these rectangles have to have the same. They don't have to, but to make the problem easier, we want to make them have the same length of width. To do that, we do b minus a over n, and that is what delta x is equal to. So this delta xi is b minus a over n. For our problem, that goes from 0 to 1, it's going to be 1 minus 0 divided by 3, or 1/3. So each rectangle has length 1/3. Now the height of the rectangles is given by the function evaluated at the either the left point, the right point, or the midpoint. This is 1/3, this is 2/3, and this is 3 over 3. So you have choices here. You could go with the midpoint, you could go with the right point for the Riemann sum, or the left point. So if I were to go and do this problem, I like to use the midpoint only because the midpoint gives me a more accurate representation. So if somebody asked me to write the 3-term Riemann sum of this on the train, then I will say that that is equal to um, the sum from n equals 0 to 1 of f of xi times delta x, which is 1/3, and the xi's are actually the midpoints here. If I was using the midpoints, if I was not using the midpoints, I could use the right endpoints, which is 1/3, 2/3, and 1, or the left points, which is 0, 1/3, and 2/3, or the midpoint. So this is equal to, anyway, 1/3 times f of x1 plus f of x2 plus f of x3. It's just the height, which is f of x1, f of x2, and f of x3, times the width, which is 1/3. Now, what is the height for each one? Well, again, if I use the midpoint, then I simply have to find the midpoint at each value here. So like here, here, and here. So for the first one, it's going to be 1/6. So this is going to be f of 1/6. So that's half of that. So if I write it as 1/6, so it's 1/6, it's 2/6, it's 3/6, so it's 1/2. So f of 1/2. Yeah. This is gonna be 4/6 and then 5/6. So f of 5/6. And that's the solution. This is my 3-term Riemann sum. It's just the height, again, that I got by using b minus a over n. That's just not the height, the width, that's the width of each rectangle times the height of each rectangle. But the height is determined by which method you use. I chose to use the midpoint because the midpoint is the more accurate. You could have also used the right or left endpoints. The problem may specify which method to use, so you need to be able to know all three. Midpoint is probably the more annoying one because you have to know how to find the midpoint. You could use the midpoint formula for this. Like for example, if you were to find the midpoint between 2/3 and 1, then you simply add them up and divide by 2. So this would have been 5/3 divided by 2, which is the same thing as 5/6, which is what I have for here. Right. So that's probably the second most annoying problem in the final. Again, if you were to use the right endpoint, then this will be f of 1/3, f of 2/3, and f of 1, because these are the right endpoints of each rectangle. 1, 2/3, and 1/3. And if you were to use the left point, so this is a right sum, and the left sum, it would have been 1/3 times f of 0 plus f of 1/3 plus f of 2/3. Okay, so you have at least 3 different options of how to go about this Riemann sum problems. We don't have to evaluate it, so you don't have to actually plug in into the square root of 1 plus x squared and find out what these values are. You just have to write it. For the paper exam, for the MyLab exam, you probably will have to solve. So if you were to solve this, you just have to plug in and multiply. So like for example, you'll plug in 0 into x squared, and then you're going to have the square root of 1, which is 1. Then you'll do 1/3, 2/3, and so on, and multiply all by 1/3, and then add them up together. So at that point, it's just arithmetic. So the last 3 problems now. So question number 18, we have to find the area under the curve of y equals 5 minus 2x squared from x equals 0 to x equals 1. And this is just a definite integral. Just remember the definite integral we saw by the fundamental theorem of calculus will give us the area under the curve. So this is equal to the integral from 0 to 1 of the function f of x, which is in our case 5 minus 2x squared dx. So if we wanted to find out what the area is, we have to use the fundamental theorem of calculus. So we have to first take the antiderivative, find what the antiderivative is, and then plug in the limits of integration. So the antiderivative of 5 is 5x. The antiderivative of negative 2x squared is negative 2x cubed over 3, and we are evaluating this from 0 to 1. Now, by the fundamental theorem of calculus, this is actually equal to f of b minus f of a. What that means is the antiderivative, which we just found, evaluated at b, which is this upper value here, minus the antiderivative evaluated at a, which is this lower value here. So what we have is 5 times 1 minus 2 times 1 cubed over 3. That's this f of b piece, minus f of a, which is 5 times 0 minus 2 times 0 cubed over 3. Well, this right part is just 0. This right here is just all 0. So we just worry about the left side, which is 5 minus 2/3. 5 minus 2/3 is the same thing as 15 minus 2 over 3, which is equal to, let me not do it up there, I'll do it down here. 15 minus 2 is 13, so this is 13 over 3. So it doesn't factor more, it doesn't simplify more than that. But that is the area under the curve of 5 minus 2x squared from 0 to 1. So it just happens to be a definite integral. Finally, problem 19. Actually, no, I shouldn't say finally. There's one more problem. For problem 19, it's a simple problem. For this problem we have to use the second fundamental theorem of calculus. So here we are asked to evaluate the derivative f prime of x of the function f of x defined by f of x is equal to the integral from 0 to x of 1 over radical 1 plus t cubed dt. Now, I told you that when we had to take the derivative of something like this, by the second fundamental theorem of calculus, what will happen is the following. If you do this, doing d dx of f of x equals to the integral 0 to x of 1 over radical 1 plus t cubed dt, by the second fundamental theorem of calculus, this is just going to be equal to 1 over radical 1 plus x cubed. Okay, basically what happened here is that the antiderivative and the derivative cancel out. This upper limit of integration gets plugged into the variable, and you will be done. That will be what the derivative is. If you wanted to do this the correct way, the long way, without just applying the theorem, then what you will have to do is the following. The first thing you will have to do is to get rid of the integral sign by taking the antiderivative. This antiderivative may be difficult to take. In fact, for this particular problem, if we do a u sub, if you let u be 1 plus t cubed, then du is going to be equal to 3t squared dt, and there's no 3t squared anywhere there, so you cannot use u sub to solve this. In fact, this looks more like a trigonometric substitution problem that you will see in calculus 2. So you cannot use a u sub, which is all the tools that we have for this class besides the second fundamental theorem. Yeah, even if I use the chain rule, it probably will not work. So yeah, the second fundamental theorem works. It just tells you that you cancel these two out because I'm taking the derivative of an integral. So the operations cancel each other out. And we just get, this is our solution. The function, but evaluated at the upper limit of integration. Finally, question 20, where we finally get to use the u substitution that we learned last. We just have to simply evaluate the integral x times sine of x squared dx. This is an indefinite integral. Notice that there's multiplication here, and we have to use a u substitution here. We could let u be x squared, meaning this inner function. Then the derivative du is going to be 2x dx. Notice that I have x dx here. I don't have 2x dx. So what I could do is I could divide both of these sides by 2. So I got 1/2 du is going to be equal to x dx. So now I'm good to go for my substitution. My substitution is going to be the integral of sine of u times 1/2 du, which is the same thing as 1/2 times the integral of sine u du. Remember, the antiderivative of sine is negative cosine. Let's just remind ourselves of this. The derivative of sine is cosine of x. The derivative of cosine of x is negative sine of x. So the derivative of negative cosine of x is positive sine of x. So I have 1/2 times the antiderivative of sine of u, which is negative cosine of x, or negative cosine of u in this case, plus c. But I know what u is. U was x squared, so I just substitute back in. So this is equal to negative 1/2 cosine of x squared plus c. And that will be the solution. So these are all of the types of problems that you can expect on the final exam. The final exam will be similar to this review, at least in the topics that you can expect to see. They're definitely not going to be the exact same problems. I could guarantee. But the topics, the range of topics that you could expect to see will be exactly the ones that you see here. I have to take the derivative, all of the derivative rules, power rule, general power rule, chain rule, quotient rule, product rule, the applications of the derivative, the tangent line problem, implicit differentiation, velocity, acceleration, and position problems. You can expect to see problems on continuity. You can expect to see problems that will have you use the fundamental theorem of calc and the second fundamental theorem of calc. You can expect to see problems that use the limit techniques that we have found, the plug-in method, limits at infinity, infinite limits, the squeeze theorem. You can definitely expect problems that use the mean value theorem, the extreme value theorem for finding the max and mins of functions. You can definitely expect problems that use the first derivative test and the second derivative test in the final. And you can definitely expect problems that use the Riemann sum, the indefinite integral, the definite integral, and u substitution. So these are all of the topics that you can expect to see. And of course, related rates and optimization. I wish you luck on the final. I hope that you review all of these topics and you practice. And until the next time.